so we're going to do a special recording here. Do you guys remember the question of the cars on the wall? Cars on the wall? You guys saw the video of the motorcycles and the car. Redraw this. Okay, so there was a very steep bank. Draw this very steep again. Really, no, from this point of view, we got the taillights of the car, the back windshield, here's the wheels. Okay. And this was on a very steep banked road, but it was like curved, right? So it's like cutaway where here's the central axis. And the car had some speed, call it v, now as it's turning, right? So not constant velocity because it's always changing its direction, but a constant speed, maybe the speedometer is reading thing, to maintain a constant radial size. So this distance is r. Okay. What speed would you need to maintain that constant radial size? Right. Now I set this up with you guys, but I never solved it. Let's go ahead and solve this out because there's actually something pretty cool I want to show you about those two. Right? So do you guys remember what the two forces on the car were? If there's no friction, let's ignore friction. Even if this is iced over, we can still get an answer. Right? What's one of the forces on the car? It's weight. Yeah, it's weight. So draw a down force. I'll label it. Let's just call it the classic mg because this is really a centripetal force question. So let's call it mg. Okay. What's the other force on the car? The normal force. And if this is a really steep wall with an angle of about 60 or 70 degrees, that means the normal force is getting almost like horizontal, isn't it? Okay. Which force is bigger, the weight or the normal force in this context? Has to be the normal force. The normal force is actually pushing more than the car's weight. Right? Like if you had a scale on the wall and you could read the force between the car and the wall, if the car was at rest on a flat surface, the normal force would just be its weight. Okay? And if it's moving around, the normal force has to be more than the weight. Because if you split this weight into components, say, well, the normal force. If the normal force you split into components, then the normal force is partly holding the car up and partly pushing the car into the circle, isn't it? Okay. And the amount that it pushes the car up is exactly equal to the weight of the car, because the force, the vertical force has to zero out. See how the force up and the force down have to balance out? Is that? Okay. And the horizontal component of that normal force, isn't that actually what's pushing the car into a circle? That's called the centripetal force. That's your mv squared on r. Right? Guess that? So if the car goes any faster, it's going to tend to drift up the incline. If it goes slower, it's going to tend to drift down. But if everything's in balance, from a dynamic equilibrium point of view, then that's what you've got going on. Okay? Now, it's not true static equilibrium because there is a net force, and then net force is this one right here. Okay? But remember, this centripetal force is never a force unto itself. It's always supplied by one of your classic forces. If AP asks you this question, what is the centripetal force? I'll tell you what the answer is, because I assume it asked this exact question before. The answer is, what is the centripetal force? It's the horizontal component of the normal force, and that would be the answer, like a multiple choice answer. Okay? And isn't that equal to, oh, well, I need to label theta. Can you guys see by eyeballing it, which of these angles is theta? Is it this top angle, or is it this bottom angle? Yeah, it's this one right here. So this is also theta. So this is like 65 degrees, this is 65 degrees, something like that. So wouldn't this be normal force times sine of that angle? Isn't that exactly what that is? Okay. Oh, and if that's true, then isn't this one normal force times cosine of that angle? Ooh, I see a system of equations that wants to be set up and answered. You guys see what I see? I'm seeing this, that mv squared on r is equal to normal force times sine of the angle. Remember our ultimate goal, figure out what does that mean. And I also see that the weight of the car is equivalent to the cosine component of the weight. Get that? This right here is your system of equations. System of equations right there. Is that? And our ultimate goal is, what is the speed of the car? How fast do you have to keep it going to maintain a constant radial size? how are we gonna solve that system? I'll show you guys a fast way to solve it. Or what do you guys think? Can you guys think of a fast way to solve this? Substitution, elimination. I'm gonna divide one equation by the other. Is it okay if I take one of these and just straight up divide it by the other? I can do that, right? Okay. If I do that, you guys see that what's gonna cancel out? The mass of the car. Hey, remember the very heavy car and the very light motorcycle need like the same speed to stay in orbit? Right? Ooh, that's what that means. What else cancels? Normal force. Right? So if I clean this up a bit, I've got v, which I'm solving for squared, divided by this r and this g, is equal. Oh, yeah, tangent. Yeah, you guys see that? Sine over cosine is tangent. So 2 algebra steps from solving this. Multiply the RG, take the square root. That's the answer. The speed of the car must be the square root of r times g times tan of the angle. That's it. That is the answer. All right. Guys good there? Now, everything that we just did is from an inertial frame of reference. I'm going to write that. Inertial frame of reference. Let's say our point of view, like as an outsider seeing this thing spin from the outside, right? Which is exactly how AQ wants you to solve it. Good so far? All right. I'm going to tell you guys something that I shouldn't tell you, and I'm not officially telling you anything that I'm going to tell you in the next few minutes here. So if you ever, I don't know, just start ignoring me and playing on your phone, the next few minutes is the time. I'm going to show you guys some physics black magic. You guys want to see some physics black magic? I want to show you a different way to solve this. That, again, don't ever do this on an AP exam because you'll lose points because they don't accept black magic answers. Just for you guys. And you didn't hear this from me.
Oh, I just happened to hear it from another random physics.
Yeah, I don't know where. I searched some sketchy corner of the internet. All right. Now, you guys know that there's no centrifugal force pushing the car out, right? You guys know that. There's a centrifugal force holding it in. There's no centrifugal force holding it. But if you're blindfolded, you might feel like there's a centrifugal force, right? So, I don't know. What if we just kind of put one there? What if we pretended that you blindfolded inside that car felt what you perceived to be a centrifugal force? I'm going to call this a, black magic force, a fictitious centrifugal force. Okay. Do you guys remember for inclines, I usually had you guys introduce Cartesian systems that run parallel perpendicular to the surface? Okay. We're going to do that on this. Now, notice I did not actually do that on the last one. You guys see that? For the inertial frame of reference. I didn't actually do this, but for this explanation, I'm going to do that. So introduce a Cartesian system, parallel perpendicular to the surface, like we usually do for inclines. Okay. And I say, this fictitious centrifugal force, which might be quantified as mv squared over r. Okay. Solve for that v. The same r, the whole deal. This thing's going around the loop. Central axis. Got some value r. All that. Okay. I'm going to split up this fictitious centrifugal force into components and say, well, also, what is it even being provided by? I haven't even talked about that yet, but suppose it was there. It'd be partially pushing the car into the surface and partly trying to make the car drift up the incline, wouldn't it? Because if the car were to go faster, then this would increase and then the car would kind of drift up the incline. Okay. Do you guys think that this angle right here is the same thing as this angle? It's the same thing? It kind of looks like it, doesn't it? Right? And if that's true, then isn't this equal to the sine, or sorry, the cosine component of mv squared over r? So that'd be mv squared on r times cosine of the angle. That would be the case, right? But the car isn't drifting up the incline because it also has some weight. So let me throw a weight on the board here, some weight. Mg for weight. Okay? And the weight, I could do a similar story. I could break this into components. So its weight is partially pushing the car into the incline, okay? And also partially trying to make the car fall sort of down the incline, okay? And the angle theta actually pops up here. Wouldn't this be the sine component of the weight? mg sine theta? That be true? Okay. Now this whole setup, remember this is from a rotating frame of reference. Okay, good so far? Okay. And if the car is not moving up or down the incline, then don't these two components have to be equal to each other? Can that be true? Okay. So maybe I could say something like this. I could say that, I'm just gonna run out of paper. All right, burn more paper. Could you guys say that maybe mv squared on our cosine theta is equivalent, that's the force trying to make the car drift up the road from this frame of reference, is it held in place, in check by mg sine theta? Could be the same thing, right? Okay, so, and then, oh, well, the mass is still going to cancel out just like before. I'm solving for this v, so I'm going to cross multiply the r, divide down the cosine, so I get v squared is equal to, let's see, that'd be r times g times, sine over cosine. Hey, that's tangent. And then to get v, all I have to do is take the square root. Oh, look at this.
Black magic.
That is the same answer as we got before. Dun, dun, dun. Physics black magic.